Article 445.14 of the National Electrical Code states that a generator must connect to the premises wiring system through a listed transfer switch, or other approved automatic or manual transfer equipment. Article 445.14b requires the output conductors of the generator to be connected to the transfer equipment, ensuring the ampacity of the output conductors is at least equal to the ampacity of the conductors supplying power to the transfer equipment from the utility service. Article 705.6 states that where multiple electric power production sources are interconnected, each source must be provided with a transfer switch or other approved means to connect and disconnect the source from the interconnected system. Analyzing the described installation, if the transfer switches are installed between the generators and the manual transfer switch, this setup aligns with National Electrical Code requirements, as each generator connects to the manual transfer switch through a transfer switch. However, if the transfer switches are located between the manual transfer switch and the sub-panels, the installation would not be compliant, as the generators lack direct connection to the manual transfer switch via transfer switches. Based on this analysis, it is advisable to consult with a qualified electrician to verify the installation's adherence to National Electrical Code standards. The electrician should assess the positioning of the transfer switches and implement necessary adjustments to ensure compliance. For optimal practice, directly feeding the manual transfer switch from both generators and subsequently installing another panel is recommended. This approach facilitates a more dependable and adaptable power distribution network. Let's delve deeper into the National Electrical Code requirements concerning generators and transfer switches. Article 445, specifically Section 445.14, addresses the connection of generators. Subsection A mandates that the generator be connected to the premises wiring system through a listed transfer switch or other approved automatic or manual transfer equipment. This requirement ensures that the generator is properly isolated from the utility power grid, preventing backfeed and potential hazards. The transfer switch allows for a safe and seamless transition between the utility power and the generator power during an outage. Now let's examine subsection B of Article 445.14. This section focuses on the ampacity of the output conductors of the generator. It requires that the ampacity of these conductors be at least equal to the ampacity of the conductors supplying power to the transfer equipment from the utility service. This requirement ensures that the generator is capable of carrying the full load of the connected circuits without overheating or causing a fire hazard. In addition to Article 445, Article 705 of the National Electrical Code also provides relevant guidance on interconnected electric power production sources. Section 705.6 specifically addresses the need for transfer switches or other approved means to connect and disconnect each source from the interconnected system. This requirement applies when multiple electric power production sources, such as generators, solar panels, or wind turbines, are interconnected. The transfer switch or other approved means allows for the isolation of each source, preventing conflicts or interference between the different sources. In the installation described, the two generators are interconnected through the manual transfer switch. The critical question is whether the transfer switches are installed between the generators and the manual transfer switch or between the manual transfer switch and the sub-panels. If the transfer switches are installed between the generators and the manual transfer switch, this configuration would likely be compliant with the National Electrical Code requirements. In this scenario, each generator is connected to the manual transfer switch through a transfer switch, ensuring proper isolation and preventing backfeed. However, if the transfer switches are installed between the manual transfer switch and the sub-panels, this configuration would likely not be compliant with the National Electrical Code requirements. In this case, the generators are not directly connected to the manual transfer switch through transfer switches, potentially creating a hazard. Based on the information provided, it is recommended to consult with a qualified electrician to verify the compliance of the installation with the National Electrical Code requirements. The electrician should carefully examine the location of the transfer switches and make any necessary modifications to ensure compliance. Furthermore, it is generally considered best practice to feed the manual transfer switch directly from both generators and then install another panel. This configuration provides a more reliable and flexible power distribution system. It allows for easier maintenance and troubleshooting, as well as the ability to isolate individual circuits or panels. In summary, the National Electrical Code requires that generators be connected to the premises wiring system through a listed transfer switch or other approved means. The ampacity of the output conductors of the generator must be at least equal to the ampacity of the conductors supplying power to the transfer equipment from the utility service. When multiple electric power production sources are interconnected, each source must be provided with a transfer switch or other approved means to connect and disconnect the source from the interconnected system. It is essential to consult with a qualified electrician to ensure that any generator installation is compliant with the National Electrical Code requirements. Let's discuss the conductor sizing aspect of generator installations as it relates to the National Electrical Code. The National Electrical Code provides specific guidelines for sizing conductors used in generator installations to ensure safe and reliable operation. Firstly, conductors must be sized to carry the maximum current that the generator is capable of producing. This is typically based on the generator's nameplate rating. The National Electrical Code provides tables that list the ampacity of various conductor sizes based on their insulation type and installation method. Secondly, the conductors must be protected against overcurrent. This is typically accomplished using circuit breakers or fuses. The overcurrent protection device must be sized to protect the conductors from overload and short circuits. Thirdly, the conductors must be installed in accordance with the National Electrical Code requirements. This includes proper support, protection from physical damage, and separation from other conductors. In the scenario described, the generator is feeding two disconnects, each with 400 amps mains. A 100 amps breaker from the first disconnect and a 200 amps breaker from the second disconnect feed a manual transfer switch, with each conductor landing on the same pole of the manual transfer switch. The conductors are sized as 35 mm squared and 95 mm squared, respectively. The other pole is fed by a 100 kilowatt backup generator with 120 mm squared conductor. The outgoing from the manual transfer switch branches off into a 95 mm squared and 35 mm squared feeder, each going to its respective sub-panel. To determine whether the conductor sizes are adequate, we need to consider the ampacity of each conductor size and the current that it is expected to carry. We also need to consider the overcurrent protection provided for each conductor. According to typical ampacity tables, a 35 mm squared copper conductor has an ampacity of approximately 150 amps. A 95 mm squared copper conductor has an ampacity of approximately 250 amps, and a 120 mm squared copper conductor has an ampacity of approximately 300 amps. The 100 amps breaker from the first disconnect is adequately protected by the 35 mm squared conductor, as the conductor's ampacity exceeds the breaker's rating. Similarly, the 200 amps breaker from the second disconnect is adequately protected by the 95 mm squared conductor. The 100 kilowatt generator is capable of producing approximately 417 amps at 240 volts or 240 amps at 480 volts. The 120 mm squared conductor feeding the manual transfer switch from the generator is likely adequate, assuming the generator is not operating at its maximum output for extended periods. However, it is important to verify the generator's actual output and the conductor's ampacity to ensure compliance. The 95 mm squared and 35 mm squared feeders outgoing from the manual transfer switch appear to be adequately sized for the loads they are serving, assuming the loads are appropriately balanced and do not exceed the conductor's ampacity. Overall, the conductor sizes in this installation appear to be generally adequate, but it is important to verify the actual loads and generator output to ensure compliance with the National Electrical Code requirements. A qualified electrician should perform a thorough load calculation and conductor ampacity verification to ensure that the installation is safe and compliant. Let's discuss the implications of interconnecting multiple power sources, such as generators. through a manual transfer switch. When multiple power sources are interconnected, it is essential to ensure that they are properly synchronized and controlled to prevent conflicts or damage. The National Electrical Code provides specific requirements for interconnected power production sources in Article 705. One of the key requirements is that each source must be provided with a transfer switch or other approved means to connect and disconnect the source from the interconnected system. This allows for the isolation of each source, preventing backfeed or other undesirable interactions. In the scenario described, the two generators are interconnected through the manual transfer switch. It is crucial to ensure that the generators are properly synchronized before they are connected to the manual transfer switch. Synchronization ensures that the voltage, frequency, and phase angle of the two generators are closely matched. If the generators are not synchronized, connecting them together can result in a large surge of current, which can damage the generators, the manual transfer switch, or other equipment. There are several methods for synchronizing generators, including manual synchronization and automatic synchronization. Manual synchronization involves using instruments to measure the voltage, frequency, and phase angle of the two generators and then manually adjusting the generator controls until they are synchronized. Automatic synchronization uses electronic controllers to automatically synchronize the generators. In addition to synchronization, it is also important to ensure that the generators are properly load shared. Load sharing ensures that each generator is carrying its fair share of the total load. If one generator is carrying too much load, it can overheat or become unstable. Load sharing can be achieved through various methods, including droop control and isochronous control. Droop control involves setting the generator's frequency to droop slightly as the load increases. This causes the generators to automatically share the load proportionally to their size. Isochronous control involves using electronic controllers to maintain a constant frequency, regardless of the load. This requires communication between the generators to ensure that they are sharing the load properly. In the scenario described, it is important to ensure that the two generators are properly synchronized and load shared to prevent any problems. A qualified electrician should perform a thorough analysis of the installation and implement appropriate control strategies. Let's examine the best practices for designing and installing generator systems. Proper design and installation are crucial for ensuring the safety, reliability, and performance of a generator system. Firstly, it is essential to perform a thorough load calculation to determine the size of the generator required. The load calculation should take into account all of the loads that will be connected to the generator, including lighting, appliances, HVAC equipment, and motors. The generator should be sized to handle the peak load with some margin for future expansion. Secondly, the generator should be located in a well-ventilated area. Generators produce heat and exhaust fumes, which can be harmful if not properly ventilated. The generator should be located away from flammable materials and should be protected from the elements. Thirdly, the generator should be connected to the electrical system through a transfer switch. The transfer switch allows for a safe and seamless transition between the utility power and the generator power during an outage. The transfer switch should be sized to handle the full load of the generator. Fourthly, the generator should be properly grounded. Grounding protects against electrical shock and provides a path for fault current to flow back to the source. The generator should be grounded in accordance with the National Electrical Code requirements. Fifthly, the generator should be regularly maintained. Regular maintenance includes checking the oil level, coolant level, and battery voltage. The generator should also be started and run periodically to ensure that it is in good working order. In the scenario described, it is recommended to feed the manual transfer switch directly from both generators and then install another panel. This configuration provides a more reliable and flexible power distribution system. It allows for easier maintenance and troubleshooting, as well as the ability to isolate individual circuits or panels. In addition, it is important to ensure that all of the components of the generator system are properly sized and installed in accordance with the National Electrical Code requirements. A qualified electrician should be consulted to ensure that the generator system is safe, reliable, and performs as expected. Let's analyze the specific components mentioned in the scenario and their roles in the overall system. The scenario describes the generator feeding two disconnects, each with 400 amps mains. These disconnects serve as the main points of isolation for the generator system. They allow for the disconnection of the generator from the electrical system for maintenance or repairs. The 400 amps rating indicates the maximum current that the disconnects are capable of handling. From the disconnects, a 100 amps breaker from the first disconnect and a 200 amps breaker from the second disconnect feed a manual transfer switch. These breakers provide overcurrent protection for the circuits feeding the manual transfer switch. The 100 amps and 200 amps ratings indicate the maximum current that the breakers are designed to carry without tripping. The manual transfer switch is the central component of the system. It allows for the selection of either the generator power or the utility power to feed the load. The manual transfer switch is manually operated, meaning that someone must physically switch between the two power sources. The conductors connecting the breakers to the manual transfer switch are sized as 35 mm squared and 95 mm squared respectively. These conductor sizes must be adequate to carry the current demanded by the loads connected to the manual transfer switch. The other pole of the manual transfer switch is fed by a 100 kW backup generator with 120 mm squared conductor. This generator provides backup power in the event of a utility power outage. The 100 kW rating indicates the maximum power that the generator is capable of producing. The 120 mm squared conductor must be adequate to carry the full output of the generator. The outgoing from the manual transfer switch branches off into a 95 mm squared and 35 mm squared feeder. Each feeder goes to its respective subpanel. These subpanels distribute the power to the various loads in the building. The 95 mm squared and 35 mm squared feeders must be adequate to carry the current demanded by the loads connected to the subpanels. In summary, each component of the system plays a crucial role in ensuring the safe and reliable operation of the generator system. The disconnects provide isolation, the breakers provide overcurrent protection, the manual transfer switch allows for the selection of a power source, the generator provides backup power, and the subpanels distribute the power to the loads. It is essential to ensure that all of the components are properly sized and installed in accordance with the National Electrical Code requirements. Let's address the specific question of whether the National Electrical Code has anything to offer with regards to this setup. The National Electrical Code is a comprehensive set of standards for the safe installation of electrical wiring and equipment. It covers a wide range of topics, including generators, transfer switches, and conductor sizing. As discussed earlier, Article 445 of the National Electrical Code specifically addresses generators. It provides requirements for the installation, wiring, and protection of generators. Article 705 of the National Electrical Code addresses interconnected electric power production sources. It provides requirements for the interconnection of multiple power sources, such as generators, solar panels, and wind turbines. In addition to these specific articles, the National Electrical Code also contains general requirements for conductor sizing, overcurrent protection, and grounding. These requirements apply to all electrical installations, including generator systems. Therefore, the National Electrical Code has a great deal to offer with regards to this setup. It provides specific requirements for the installation, wiring, and protection of generators and transfer switches. It also provides general requirements for conductor sizing, overcurrent protection, and grounding. It is essential to consult with a qualified electrician to ensure that any generator installation is compliant with the National Electrical Code requirements. The electrician should be familiar with the relevant articles of the National Electrical Code and should be able to interpret and apply them correctly. In addition to the National Electrical Code, there may also be local codes and regulations that apply to generator installations. These local codes and regulations may be more stringent than the National Electrical Code requirements. It is important to check with the local authorities to determine what codes and regulations apply to the installation. In conclusion, the National Electrical Code provides a comprehensive set of standards for the safe installation of electrical wiring and equipment, including generator systems. It is essential to consult with a qualified electrician to ensure that any generator installation is compliant with the National Electrical Code requirements and any applicable local codes and regulations.